Imagine this. You've spent years collecting research papers, e-books, and lecture notes. But every time you need one crucial fact, you're stuck scrolling through hundreds of pages. What if instead of searching, you could simply ask your library, and it would answer you instantly, citing exactly where it found the information? Well, today I'll show you how to build your own AI librarian using Langflow and Retrieval-Augmented Generation, or RAG. Hi everyone, welcome back to my channel. If you're new here, this channel is all about practical AI tools and tutorials to help you work smarter, not harder. So if that sounds interesting, don't forget to hit like and subscribe so you don't miss the next video. Okay, let's jump right into the video. We'll be using a platform called Langflow for this project. Langflow is an open-source platform that lets you build AI pipelines visually. Instead of writing a lot of code, you can drag and drop components like document loaders, vector databases, retrievers, and language models, and connect them together in a flow. This makes it perfect for building a system like our AI librarian. All right, before we jump into making our AI librarian with Langflow, let's first understand what RAG, Retrieval-Augmented Generation, actually is. At its core, RAG combines two things. One, a retrieval system which searches your knowledge base for the most relevant information. Two, a large language model, which takes that retrieved context and generates a natural answer. Think of it like an open-book exam. Instead of guessing from memory, the AI looks into your library before it answers. This approach helps reduce hallucinations, ensures more accurate results, and makes the AI feel like it's truly grounded in your documents. Let's discuss the core components of what we need to build our AI librarian and how they interact with one another. Firstly, we are going to need acknowledgement base. This is our external repository of information. It could be books, research papers, lecture notes, PDFs, websites, or any collection of documents. Most of this data is unstructured, so the first step is to prepare it for use. Next, we will be splitting the documents into chunks. Since the entire books and articles are too large for efficient searching, we split documents into smaller chunks, usually a few hundred words each. This makes retrieval more precise, so the system can pull the exact passage that matches our query, instead of entire chapters. The next step is to pass each chunk of text through an embedding model. This model converts the text into a numerical vector, a representation in multidimensional space. In this vector space, data points with similar meanings are placed close together, which allows for semantic search. In simple terms, it teaches the computer not just what the words are, but what they mean. Next, we are going to be indexing and storing the vectors created by the embedding model in a vector database. This database stores the vector, which acts as a smart index of our knowledge base. This database allows for fast similarity searches. When you ask a question, the system can quickly identify which chunks of information are most relevant. The next component on our list is the retriever. The retriever comes into play when a user submits a query. It looks into the vector database and finds the most relevant chunks of information and pulls them out. Think of it as the librarian, who knows exactly where to find the right passages for your question. Our next component is the integration layer and prompt template. Once we have the retrieved information, it moves into the integration layer. Here, the system combines our original query with the retrieved context into a prompt template. For example, instead of simply asking, "Explain relativity," the augmented prompt might say, "Using the following retrieved passages from Einstein's papers, explain relativity in simple terms." This ensures the language model answers with grounding in the actual documents. Finally, the large language model, or LLM, generates the response. It takes the augmented prompt, uses the retrieved data as context, and produces a coherent, fluent, and accurate answer. This response is then returned to the user, not from the LLM's memory alone, but based on the actual knowledge base provided. Together, these components form the backbone of retrieval-augmented generation. Now, let's put them into action inside Langflow. Now, let's build this step-by-step inside Langflow. On the left side of the screen, we have the Components section. This is where all the building blocks live: loaders, databases, models, inputs, outputs, everything you need to design your flow. Step 1. Build a simple chatbot. To warm up, let's first build a basic chatbot. I'll drag in a chat input and chat output from the components. Then, we need a model. For this tutorial, I'll be using Groq, which runs open-source large language models with great performance and, best of all, offers free usage. I'll do a full setup video on Groq in the future, but for now, you can head to groq.com, sign up, and grab your API key. Back to Langflow, I'll connect the chat input to model to chat output. That's it. We have a simple chatbot. Let's test it quickly. And as you can see, it responds immediately. Step 2. Add a knowledge base. AI Librarian build begins. Now, let's extend this into our AI Librarian. From our architecture, the first thing we need is a document loader. I'll search for File in the components and add a File Loader node. This lets us load PDFs or text files directly into the flow. Step 3. Split text into chunks. Next, we add a text splitter. Large documents are too big for retrieval, so we split them into smaller chunks. We'll use the Langflow default settings here. This ensures the retriever can pull out precise sections instead of whole chapters. I'll connect the file loader to text splitter. Step 4. Store in a vector database. For the vector database, I'll be using AstraDB, which is a really popular cloud-based vector database from DataStax. It has a free tier, it's scalable, and it integrates smoothly with Langflow. Let me quickly show you how to set up a vector database in AstraDB. Step 1. Head over to astradb.datastax.com. I'll leave the link in the description below. If you don't already have an account, you can create a free one, or simply sign in with your Google or GitHub account. Step 2. Once you're logged in, click Create Database. From the options, choose Vector Database, give it a name, and then select a provider and region. Just note that if you're on the free tier, you only get access to the US East region. Step 3. Wait a few moments while AstraDB creates your database. Once it's ready, click Generate Token. Copy this token. This is your authentication key, and you'll need it when connecting AstraDB to Langflow. Now, let's head back into Langflow. Open the AstraDB node, paste in the application token where it asks for your key, and create a collection that matches the embedding model you're using. And that's it. AstraDB is now fully connected to Langflow and ready to store your document embeddings. From here, we can flow right back into our pipeline. I'll connect the text splitter to AstraDB ingest, so all our chunks are now stored in the database. Step 5. Add retrieval. Next, we wire up the retriever. The output from the chat input is sent to the AstraDB search query node. So now, whenever a user asks a question, the retriever looks into our vector database and pulls the most relevant passages. Step 6. Parse and prompt template. Once the retriever finds relevant text, we pass it to a parser node. This extracts the key sections and hands them to a prompt template. Here we combine the user's query and the retrieved text into one structured prompt. Something like, based on the following documents, answer the user's question. This ensures our answers are grounded in the library. Step 7. Connect to the LLM. Now we connect this to our large language model. The LLM uses the context from the vector database and generates a fluent, accurate answer. Now let's put everything to the test. I'll upload 2 different documents into our system. One is research on chess, and the other is a restaurant FAQ. With both documents ingested, I'll open the chat interface in Langflow. First, let's ask a question from the chess research. Explain the classical and neural network concepts in Stockfish. The system fetches the relevant passages from my chess document and provides a clear, context-based summary. Now, let's switch over to the restaurant FAQ. I'll ask, what are your working hours and where are you located? And once again, the system pulls the exact answer directly from my documents. So you can see how this AI librarian adapts to completely different knowledge bases, whether it's technical research or customer support FAQs, and always provides grounded, reliable answers. So to recap, we learned what retrieval-augmented generation is. We explored the key technical components: document corpus, vector database, retriever, LLM, and user interface. We saw how Langflow makes it easy to connect these components into a working pipeline. And we built a fully working AI librarian that can instantly search through your personal library and give you accurate, cited answers. This is the future of knowledge access. Libraries that are not just static collections, but intelligent assistants available anytime, anywhere. If you found this tutorial helpful, don't forget to like this video, subscribe for more AI tutorials, and let me know in the comments what you'd use an AI librarian for: studying, research, or maybe personal knowledge management. Thanks for watching, and I'll see you in the next one.